Okay, so we've spent some time talking about, rejecting the null and failing to reject the null. And I've spent some time talking about critical values, okay, which come from the confidence level and the significance level. And we've talked about the test statistic, which is a unitless number that comes from your sample data. And I've kind of shown one independent of the other. Now we're going to take those two separate ideas and put them together and see how they interact together to help us come to a conclusion in our hypothesis test. Okay, so the critical value not only separates the confidence level and the significance level, but it is also a boundary between two regions: reject the null and fail to reject the null. So to give an example down below, here we've got a critical value, which is the boundary to both the confidence level area and the significance level area, as well as the boundary between the rejecting the null region and the failing to reject the null region. The reject the null region is always over the tail of the distribution. So I think I had mentioned that before, is that reject the null is always over the significance level area, right? Thus, the null hypothesis is rejected when a rare event has occurred. Okay, in hypothesis testing, one begins by making a claim, either directly or indirectly, about the null hypothesis, and one ends up by calculating whether the evidence dictates to either reject the null or fail to reject the null. So the question is, how is the decision between rejecting the null or failing to reject the null made? And the answer is by comparing either, okay, either, because there's two ways to do it, by comparing the test statistic to the critical value, because those are both unitless numbers on a number line, and you can compare two numbers on a number line. Or you can compare two areas. You can compare the size of the p-value area against the size of the significance level area. Okay, so this is an area and this is an area. Again, comparing apples to apples and oranges to oranges. So depending on the distribution that you're working with, you would compare a z-test statistic, which comes from your sample data, and compare that to a z-critical value, which generally comes from your significance level. You could compare a t-test statistic, which again comes from your sample data, and compare that to a t-critical value, which again comes from the significance level. You could compare a chi-squared test statistic, which again comes from your sample data, and compare that against the chi-squared critical value, which, guess what, comes from the significance value. Or you could compare an F test statistic, which comes from your sample data, and compare that to an F critical value, which, you guessed it, comes from your significance level. In each of these scenarios, the area next to your test statistic is called the p-value. So this is the area adjacent to the test statistic. And you compare that area to either the significance level or the significance level divided by 2. And you can kind of do that same process with any distribution. All right. Now, looking at p-values, is something that you see in more professional circles. Okay. But I think for an introduction to statistics student looking at this for the first time, it's easier to think about comparing two numbers on a number line because you have more experience doing that in your past than you have comparing two areas against each other. But at the same time, this is when you are expanding your thinking and you're expanding your knowledge and you're learning more. And this is also the right time to kind of show you how else to compare things. You don't just compare two numbers, you can compare two areas as well. So how do we do this comparison between what we glean from a sample and what our constraints are, like our confidence level or significance level constraints? So what I've done is I'm showing two separate pictures here. Okay, the picture on the left is showing the critical value boundary and everything around it, right? So we have a critical value, which is a number on the number line. That value on the number line defines where this boundary is, and that boundary does two things. So the critical value does two things. It's the defining boundary between the confidence level and the significance level, and it's the boundary between rejecting the null and failing to reject the null. Okay, all of those things go together. Now this other picture, again, is the same distribution, but now the value on the number line that we have is the test statistic. Okay, and remember, the test statistic comes from our sample data. Okay, and this test statistic also serves as a boundary. It's a boundary for the probability value, which is the area adjacent to it. So if you want to compare this picture with that one, then what we want to do is we want to superimpose them on top of each other. And that's kind of what I'm trying to show here on a two-dimensional page, is you can notice that these are the exact same shape with the exact same dimensions. And, here's the one with the critical value and the critical value boundary. Here's the one with the test statistic and the p-value. And as you take those two and you bring them closer and closer and closer together until they're completely overlapping, okay, then you end up with a picture that looks like this. So hopefully you can look at this picture and you can see those two separate pictures in it. Okay. And yeah, so this is the picture of the merged critical value and test statistic figures. So look at what we've got. We've got the critical value here, and we've got the critical value boundary there with the confidence level and the significance level. And then over here on the right, we have our test statistic value, which is the boundary for our p-value, which is this area off to the right. So this picture is missing one more thing, and that's this picture on the right here. So let me talk about this. So here's our critical value. Okay, the critical value is usually determined by the significance level. So the critical value is the boundary between the significance level and the confidence level. It is also the boundary separating the reject the null and the fail to reject the null regions. And then right here, again, we've got the test statistic, which serves as a boundary to the probability value, which is the area adjacent to the test statistic. So in this hypothetical hypothesis test demonstrated here, the following is occurring. So notice that the test statistic is greater than the critical value, right? So on a number line, here is 0, here's about 1, and here's 2. So you can clearly see that the test statistic is greater than the critical value. And another thing to notice, well, let me kind of point out what that means first. So because the test statistic is greater than the critical value, it's to the right of the critical value, the test statistic is clearly in the reject the null region. And that's how we're going to come to our conclusion, is that after the whole hypothesis test is said and done, we're going to reject the null hypothesis from the very beginning of this whole process. Now, we can do that by comparing apples to apples. How do we do it? By comparing oranges to oranges, area to area. So let me show how we do that with area. And it may be a little bit difficult to see here. But you can see that this significance level, this area of 0.2, is this orange area. But we've done significance levels enough, you know, that it's the area all the way through this tail. Okay, so this kind of red diagonal lined area, that's the area of our significance level. Okay, now in green, let me do the same thing, but this is going to be the area of our p-value. So the p-value is the area adjacent to the test statistic. So that's going to be right here. Okay. So which area is greater? Hopefully you can see that the area of the p-value, which is this smaller area right here, okay, that's less than the area of the significance level, which was all the way out here and also including the tail. So it's harder to see when those two areas overlap. Okay, that overlapping, is what's happening. If I go back to when these were separate, you can see that the significance level is this entire area from the boundary all the way out to the tip of the tail, whereas the p-value is also an area to the tip of the tail, but it's bounded by the test statistic. So when you put them on top of each other, it looks like maybe the p-value is kind of covering the significance level a little bit. Okay. All right. And, this p-value being smaller than the significance level implies that we're going to reject the null. Because when the p-value is smaller than your significance level, what region are you in? You're clearly in the reject the null region. Okay. So what many people do is, in scientific papers and stuff, they'll say the significance level is 0.05. And then they'll say, well, during the course of our research, we did a hypothesis test and the p-value was 0.02. And they know just by looking at the p-value that the p-value here is less than the significance level So you have a situation like this, and they'll say, therefore, we are rejecting our null hypothesis. So they'll do that just by comparing these two numbers and which one is greater and which one is smaller. And when you get used to it, this is a slightly easier way to think about it. But right now for you, this might be more of a foreign way. And so it may not be that easy to think about it that way. It might be easier to think of it in terms of values or numbers on a number line. And if the test statistic is greater than a critical value, the test statistic is on this side of the boundary. If the test statistic was smaller, it would be over here, and that would give you a different outcome. So it might be easier to think of numbers on a number line instead of relative areas. One way to kind of remember this idea about the p-value and the significance level is I kind of came up with a little sentence. It says, if p is smaller, reject the nuller. So if the p-value is smaller than the significance level, then reject the null. Okay, so if p is smaller, reject the nuller. Otherwise, you're going to fail to reject. Okay, so let's take this idea, and I've talked a lot about it, but it's always best to see it from scratch as an example. Okay, so let's look at an example now. Next will be a think, pair, share, but let's do an example now. So this says, find the p-value for each test and state the conclusion about the null hypothesis. So it says H1 colon P greater than 1/4. Test statistic is Z-test 2.79. Alpha equals 0.01. Okay, so you might be looking at that. Okay, what the heck am I supposed to do with this? So remember what all of this centers around. Start by drawing a picture. And what picture should we draw? This normal distribution picture. So let's start with that. Okay, and again, this is a sketch, so it doesn't have to be perfect. I would make it big enough so that you can clearly have plenty of room to draw whatever it is you need to draw. That. Okay, so what we need, let me put it off to the side over here. So it says to find the p-value. So what we need is we need a p-value. But in order to get that p-value, what we need is we need a test statistic in order to get it. So it turns out that they gave us that test statistic. So Z-test equals 2.79. All right. Let's see here. And what we also need is we need to, that's one. Number two is we need to write or come to a conclusion. So we need to come to a conclusion about the null hypothesis. All right. What we've got is the alternate hypothesis, right? And there's a couple of things that tell me this is the alternate. Number one, the inequality does not have an equality in it, right? It doesn't have equals. It's not greater than or equals to. It's just greater than. So that right away is telling me this is the alternate hypothesis. The other thing is that it's H subscript 1. And so remember, if it's written as HA or H subscript 1, that is the alternate hypothesis. Okay. So if our alternate hypothesis is that the population proportion is greater than 1/4, then what is going to be our null hypothesis? It's going to be that the population proportion, it'll have P, it'll have 1/4. Okay, but what is the complement of greater than? What is the complement to this? It's going to be less than. Why did it do that? You saw that. It just flipped my sign. Okay. It's going to be less than or equal to. And then it looks like, hmm, it looks like we have very little information, but I'm just going to go ahead and say that this is our original claim, just because that's in this problem right here. Okay. All right. So we've kind of done what we can with this. We found a use for that, right? That's going to give us our p-value. Okay, what can we do with this significance level? Well, this significance level, let's draw it in. So here is our significance level. It is 0.01, which means our confidence level is, so if the significance level is 1%, then the confidence level is going to be 99%. That's that area. And also remember that the alternate hypothesis tells us whether we've got a left-tailed, a right-tailed, or a two-tailed distribution. So if we make an arrow out of this, this is telling us that we've got a right-tailed distribution. And that's exactly what I've drawn here, right? We've got a distribution where the significance level is on the right tail. Okay. Now, what value is adjacent or is the boundary for the significance level and the confidence level? That is the Z critical value. Okay, and that's probably going to be positive because the center of the normal distribution when it's normalized is 0. Okay, so we're probably going to have a positive Z critical value. All right. And we've got two regions now to think about, right? This critical value defines the boundary between the reject the null region. And remember that the reject the null region is above the significance level on one side, and then the fail to reject the null is on the other side. Okay. Now, one of the things that was given to us here, okay, so my computer is working on something I can't quite explain. Okay. We were told the test statistic, okay, which comes from our sample data. So I'm down here, I'm gonna put Z test, and we know that that's 2.79. So when it says to state a conclusion, what it's asking for is, are we going to reject the null or are we going to fail to reject the null? That's what we got to figure out. Well, in order to figure that out, we need to compare either apples to apples and oranges to oranges. So what's an apples to apples comparison? Well, an apples to apples comparison would be the critical value to the test statistic, but we don't know what that is. We don't know what the value of the critical value is yet, but we need to compare that with our test statistic of 2.79. So right now, we don't know if 2.79 is going to be on this side of the critical value or on this side of the critical value relative to this point. We don't know. And that's comparing apples to apples. Now, if we want to compare oranges to oranges, then we're going to be comparing the significance level to a p-value, but we don't know what the p-value is yet because the p-value we have to calculate from our test statistic. So we have a few unknowns here in order to figure out whether we're going to reject the null or fail to reject the null. But you see how we were able to walk forward by first drawing this distribution here, right? And then we know something about the significance level and that it has a boundary and that the critical value is on that boundary. And the critical value separates the reject the null from the fail to the reject the null. So you see how you kind of just build out just from drawing that distribution curve first. So always start with just drawing a picture and trying to fill in the parts that you know. Okay. All right. So how do we get some of this missing information? Well, let's first get the critical value. Well, the critical value is adjacent to the significance level. So we're going to need an inverse distribution function for that. Now, since we're dealing with a z-score, that tells us we're dealing with a normal distribution. So we're going to be using inverse norm. So let's go over here to the graphing calculator and Texas Instruments. Let me turn this on, quit out of that. Okay, so distribution functions. So second vars, go down to inverse norm. Okay, so the area that we've got is going to be an area of 0.01, and that's going to be on the right. So we've got 0.01. Okay, when we're dealing with z-scores, the mean will always be 0, okay, because the center of the distribution, when we've got a z-scale, the center is the mean, and the mean always is 0 on a z-scale, and a standard deviation of 1. And we want a right tail. So I'll hit paste and enter, and we get 2.326. 2.326. So the z critical value is 2.326. Okay, so this number right here is 2.326. Now, let me do this on the numworks calculator. So for this, we're going to go to the distributions app, go down to normal with a mean of 0 and a standard deviation of 1. We want the area to the right, and the area that we have is 0.01. So we hit enter, it's going to give us the critical value right here, 2.326. Okay, gives us that little piece right there. So that looks good. All right. Now, let me go ahead and jump ahead and let's figure out what our conclusion is going to be. Okay. let me clean this up a little bit. I'm going to put everything back, but I just want to clean this up because if there's too many lines, it gets really confusing. Okay, so we have 2.326. This is our Z critical value. Now, where is 2.79 relative to 2.326? Is it less than or is it more than? Right? I think you can see that it's more than. 2.79 is greater. 2.79 is greater than 2.326. So 2.79 is just going to be somewhere here off to the right. That's where our test statistic is. And if our test statistic is right there, let me kind of clear some of this up. If our test statistic is here, it's clearly in the reject the null region. So our conclusion is going to be to reject the null. All right. Now we can do that comparing apples to apples, right? Critical score to test statistic. But what if we want to do this comparing oranges to oranges or area to area? Should probably make it apples and area, but anyway. Um, so how do we get our p-value? Well, the p-value is the area that's bordered by our test statistics. So the p-value is going to be this little piece right here to the right of 2.79. So here's where 2.79 is. So the p-value is going to be this area right there. So how do we get it? Well, now we need to use the normal CDF function. But let me use the numworks calculator first to kind of change it up. So we want the area to the right of 2.79. So I'm going to use this screen again. I want to use the area to the right, and I want it the area to the right of 2.79. Is that right? 2.79. Yep. Now, as I hit enter, it's going to find the area underneath this normal distribution curve to the right of 2.79. And I have an area of 0.0026. So we have a p-value of 0.0026. So when you look at this area and you compare it to this area, is the p-value smaller? And so in this case, the p-value, that's 0.0026, and our significance level is 0.01. The p-value is definitely smaller. And so the way it goes is if p is smaller, then reject the nuller, right? So by comparing areas, we determined we're rejecting the null. By comparing values on the number line, critical value versus test statistic, we're also coming to the same conclusion. Okay. So all of this stuff is what this type of question is asking for you to build. This is pretty much at the very end of a hypothesis test, is making this picture and coming to a determination of either rejecting the null like we did here or failing to reject the null. Okay. Let me know if you have any questions.